Okay, so welcome back. So far we have studied the first principle of thermodynamics for what we call closed system. So we have basically two cases for closed system. One is basically a closed container. The other one was any type of piston cylinder assembly. Okay? So for this type of system, I like to say the mass is constant. We derive the first principle of thermodynamics equation, Q minus work equal to change in energy. Okay? But most type of the engine or energy production system follow more the figure in which, and the best example is probably the engine of the aircraft, a turbofan. You have air, substance, air coming in, something happens here within the system, and then you have more substance coming out. Okay, so this type of system in the literature, generally they call them control volume, where this dashed line is the control volume. Personally, I call them open systems, just in opposition to the closed systems. Okay, but that's basically what we're going to do. How can we rewrite the first principle of thermodynamics for this type of system? So before doing that, what we need to define is how do we define the amount of substance going within the control volume or within the open system. So the first thing we need to look at is at the mass flow, something called mass flow. Okay, so what is a mass flow? Imagine you have some type of surface. So just think about a tube. You make a cut and you want to see how much substance is going to go through this area over here. Okay, or cross-sectional area. So the definition is that the amount of substance, so mass per unit time, which basically means mass per unit time, is equal to the density times the velocity. So this is the definition with the integral form. But in almost all cases, the area is known, so you can rewrite this as rho AV. Okay? So this is the way generally the mass flow is used in fluids. However, in thermodynamics, because of the definition that we have of the specific volume, so if you remember the specific volume, so anything that has specific means per unit mass. So the specific volume is basically the volume per unit mass. And if you notice, this is just the opposite of the density, because the density is what? Mass over volume. Okay, so the mass flow, you can write it as M equal to AV over little b. And here's where we need to be careful with the notation. So that's the main reason why I use the V bar, as you see over here, for the volume, because that V over here is not the volume, but the velocity. So in many textbooks, they refer to the product AV as the volumetric flow rate, where here A is the area, the cross-sectional area, V is the velocity, is not the volume, and letter V is the specific volume. Okay, so the units are what? If we look over here, would be easier. Would be densities kilograms per cubic meters times area, meters to the square, times velocity, meters per second. So, as expected, what should be the units for this, which is mass per unit time? See, this one will cancel. So basically at the end, what we have is kilogram per second. All right. So now that we know how to define the amount of mass going in here, let's say, and in and out, we are able to define this type of system. Okay, so let's look at the mass flow rate. This is basically the same thing, it's very similar, but it helps for the understanding. So imagine we have a random volume, okay? Then in this side we're gonna have mass flow going in, and on this side we're gonna have mass flow exiting, okay, going out. And this will be our open system or our control volume. Okay, so what happens if, let's say this is a pipe here that has an inlet and an outlet, but the pressure at which the water goes in or the fluid goes in is different than the one that goes out. So in that case, you have what is called here, you might have a change of the amount of the time inside the control volume in function of time. So that change in mass should be equal to what? So if we say the fluid going in is positive and the fluid exiting is negative, would be ME minus M exit. Okay, so in this class, however, you will see that we don't really care about what is the pressure, if you want, the flow going in and out. In 99.9% of the cases, it will be assumed to be the same one. Okay, so if it's the same one, that means that the amount of mass within the control volume or the open system is going to be conserved. So that's what is known as for steady state. So basically it means same amount of mass going in as going out. What's going to happen? dme dt for the control volume will be equal to 0. So that what's going to happen? The amount of mass flow going in needs to be equal to the amount of mass flow going out. And this is basically known as the conservation of mass. All right. So now that we know this, we can kind of do something similar for the for the first principle of thermodynamics for an open system. So recalling the first principle of thermodynamics equation, what do we have? Heat minus work equal change of energy. Okay, so in this problem, again, since we have mass going in and out, we need to rewrite this expression in function of time. So for the control volume, this becomes dq dt minus dw dt equal to d dt of delta E. Okay, or this will be q dot. So this is heat transfer. Amount of heat per unit time is heat transfer. Work per unit time is power. And this will be rate of energy change. I just put the dot over here. All right. Where in this equation, what is the rate of energy change? We have change in kinetic energy per unit time plus change of potential energy per unit time plus the change in internal energy per unit time. So basically what we need to do is add the m to these terms over here. Okay, to all these terms. Alright, so there we go. We have, let me just rewrite this equation. Q minus power equal change of energy. So over here, we can just rewrite this as heat transfer minus power equal to change of energy. So the energy can change in function of what? The kinetic, potential, internal. So the kinetic, let's say, will be, so this will be equal to energy out or exit minus energy in. Okay, so this will give us what? Heat transfer minus power will be equal, first the kinetic energy will be 1/2 m dot exit v exit square. So it will be the kinetic energy plus m dot g. Instead of h, I'm going to use the letter z. Z exit, so kinetic potential, plus m dot exit u exit for the internal energy. Okay, so this will be the E exit, and we have something similar for the internal energy. For the incoming energy, oops, this is, yeah, E u dot I, sorry, I over here for inlet. Okay, so we're almost done over here. And again, for the, this is work per unit time, so it's power, so we're going to have two terms. We're going to look at one term, just going to be the work, the power you can put in or out the control volume, and the other one will be work per unit time done by pressure. So if you remember, the work done by pressure was equal to integral of P dV volume. So this is V is the volume. Okay, so I can rewrite here that the work or the power will be equal to the one of the control volume plus P exit V exit minus P inlet V inlet. Okay, on the equation. So now what I'm going to do is substitute I'm just going to substitute this equation into this equation here. So that what do we get? We're going to get Q minus control volume. This term can move to the other side, so I can just add it to this one. So this will become what? Oops, this will be just the work, so I'm not adding per unit mass. So let me just add one thing over here. Sorry for that. Okay, let me just rewrite this equation to make it a bit more clear. So basically, you're going to have the work or the power will be equal to this plus M exit PE VE minus M inlet PE V inlet. Forgot the mass flow to make it per unit time. So now I can go and substitute the star equation into the big equation over there, so that we get the following equation. I want to start simplify it as factor out the amine will be V exit dot over 2 plus GZE, so kinetic potential internal plus work done by the pressure minus the M internal V internal square over 2 plus GZ inside plus U I VI. Okay. All right. So now comes the important part. So if you recall, recalling, what is enthalpy? The enthalpy was defined with the letter H and was equal to what? Internal energy plus the work done by the pressure. So if you look at it, this is actually what? This is enthalpy, and this is enthalpy over here. All right, so now we are ready to write down the final form of the equation, which is heat transfer minus power will be equal to M exit of V exit square over 2 plus G Z E plus HE minus mass flow going in square over 2 plus G Z in plus H E. Okay, almost there. Now, because of the conservation of mass in almost every single problem, what are you going to have? That the mass flow going in needs to be equal to the mass flow going out. And we can just call both of them by m. So we write in the above equation we have Q, so heat transfer power will be equal to m dot, and now we can couple them, so it will be change in enthalpy. Okay. Ooh, I forgot one term here. No, it's good. We are good. Plus change in kinetic energy plus change in potential energy. Okay. We write it once more over here, just so that I have space to make a draw a line around it. Of inlet plus m dot over 2 velocity square in the square plus mg. Okay, now we're done. So basically this is the form of the first principle of thermodynamics for an open system. That's the way I like to call it, in opposition to closed, but in most textbooks is known as a control volume. Okay, I will stop over here because I don't want to make this video too long.